And then welcome everyone to the Winds and Currents webinar. Today we have Shikhar from the University of Rochester, who is going to talk about the disproportionate role of small-scale winds on mesoscales and spurious eddy killing from resolution mismatch. Shikhar is a graduate student who is just finishing up and headed to Woods Hole as a postdoc. I'll let you take it away, Shikhar. Thanks for doing this.
Thank you, Sarah, and thank you for providing me this opportunity to tell about this disproportionate role of small-scale winds and mesoscale and spurious killing from resolution mismatch. This talk is mainly coming from two of the papers, one in Advances from 2021 and one that has been submitted and is under review. And this work is the result of collaboration with Matthew Heck and Matt Meltridge from Los Alamos National Lab, and we acknowledge the grant from NASA and NSF. So the introduction. So first, we know that the wind is the major source of energy for maintaining the global ocean circulation. In fact, 1 terawatt of the power comes from the wind to maintain this global ocean circulation. And for review, let us look how the wind in the atmosphere looks like. And we can see that the atmospheric flow is multi-scale in both time and length scales. Similarly, if we look to the flows in the ocean, we'll see that the flows in the ocean is also multi-scale. It has large-scale gyres and small-scale mesoscale eddies. If we look to these two videos, what we'll see is that the flow in the ocean and the atmosphere are in different time scales and length scales. The ocean has flow in shorter spatial scales, while longer time scales, while the atmosphere has the flows at more longer spatial scales and shorter time scales. So the motivation is, how is the physics of air-sea coupling, particularly mechanical coupling, with this difference in time scale and length scale? So I'll be trying to revolve around this question and use wind work as the diagnostic of the multi-scale coupling. So the wind work is scale dependent, as we can see from these two pictures here. On the left-hand side, this is the wind work on the large scales, and we can see that it is mostly positive, while the wind work is negative, and it is at the small scales. So the wind work has scale dependence. So I'll be trying to look into, does the resolution, the difference in the time scales and length scales, or the difference in the resolution of the sampling, because we might want to sample the atmosphere in a more coarser grade while more frequently, while for the ocean side, we might want to sample less frequent, but in a more high resolution grade. So would that affect this wind work? And I'll be particularly focusing on the wind work at the small scales. So before I'd like to show you the outline of this talk, I'll be talking a bit about the literature review, and then I'll be talking about my methodology. And then I'll be talking about the eddy killing, which is the wind work on the small scales. And I'll be talking about how the difference in the length scales and time scales and the resolution mismatch in sampling those data could affect this wind work. So first, the literature review. So I'm going to explain why the wind work at the small scales is negative, and it's the mechanism of the well-known mechanism of the eddy killing. Let's assume that there is an ocean eddy, and over it there is a constant wind. This ocean eddy feels wind of different relative strength. So the relative winds with respect to this ocean is smaller, where the wind and the ocean are in same direction, while the relative wind is larger, where the wind and the ocean are in opposite direction. This causes larger but negative drag on this side, while positive and smaller drag on this side. And as a result, the total network on this oceanic eddy is negative. So the wind work to this eddy would be negative, and this is called eddy killing. So to separate this eddy killing from the wind work at large scales, we need to understand what the oceanic flow constitutes of. The oceanic flow may contain a constant flow, meanders and waves, and eddies of different shapes and sizes, and so many things. So how do we separate the eddy killing from the wind work at large scales? So typically this is done with Reynolds averaging, where we take the time average of wind stress and the time average of ocean surface velocity, and then dot product it to say that it is power at large scales. And similarly, we dot product the fluctuations of the stress with the fluctuations in the ocean surface velocity to say that it is a power to small scales. But the question here is, does this quantity tau dot u prime really represent eddy killing? So what about the waves? Doesn't it represent waves? What about the standing eddies? The standing eddies will have u prime to be 0. So, but the cartoon that I showed you in a few slides ago should have eddy killing with even with the standing eddies. Previous studies have measured this quantity tau prime that u prime, and Hughes and Wilson, this figure comes from Hughes and Wilson 2008, and they have measured this quantity tau prime that u prime to be positive 9.3 gigawatt. Similarly, Scott and Sue measures it to be 42 gigawatt. Once 1998 measures to be 40 gigawatt. So from this values, it is evident that the mechanism that I showed you a few slides ago by this cartoon, which was expected to be negative, is not negative, and this cannot represent eddy killing. So how the other studies have estimated this eddy killing? Renaud et al. 2017 measures this through a statistical method where he finds a coupling coefficient S here as a regression, linear regression between call of wind stress and the vorticity, so the call of the ocean surface velocity. And from this coupling coefficient, he finds that the eddy killing is minus 48 gigawatt. Similarly, Su et al. Explicitly detects the eddies and finds it's 27 gigawatt, minus 27 gigawatt. So this is consistent with the explanation of eddy killing. So now I'm going to tell you how we can improve this and what we are still missing. So what we are still missing here is, we know that at large length scales, the wind provides energy, while at smaller length scales, the wind extracts energy. So what is the scale dependence of this? Is there a length scale where these two processes are separated? What is the variability of this eddy killing? What is the mathematical term for the eddy killing which fits in the energy budget equation? The linear regression and the explicitly detecting eddy methods is a very good method of finding eddy killing, yet it does not fit into the budget equations. So what is the mathematical term for eddy killing which fits into the budget equation? And we still have the questions of what physics are resolved, and do unresolved physics causes large biases, or the resolution causes biases. So now I'm going to talk about the methodology. So we have chosen the method of coarse graining to study the scales of wind forcing. So coarse graining basically is a spatial filtering where we pick a length scale L, as any flow consists of a multiple scale, which is a length scale L. And after we apply the filter, we'll get rid of the scales that are smaller than L, and the scales only larger than L remains. So we also have the freedom to choose this L. We can slide this L to any length scale and then choose our length scale. So we do this. This is a method that is particularly very commonly used in turbulence and LES. And the filtering is defined by a convolution of a field U with a kernel G here. So this is how the convolution looks like in 1D. So if our field is this small thin line, after the convolution, we'll have the small scales removed and only the large scale remaining after filtering. And this U prime is the residual. So this thin line here is the U prime, which is the residual after the convolution. Here, one thing we have to note is that the filtering, unlike Reynolds averaging, even after we filter the residual, will not get a 0 value, while in Reynolds averaging, we'll get this equals to 0. Well, this is also dependent upon the type of the kernel we choose, but in general, it is not 0. So there's again another problem with coarse graining in sphere, because the filtering, the unit basis vectors in the spherical surface changes at each location, or any non-divergent field becomes divergent after filtering, because straightforward convolution does not commute with derivative. So Louis et al. 2019 has developed a method which preserves this commutation with the filtering operation, and the non-divergent field in a spherical surface remains non-divergent even after filtering. So we have used this method to coarse grain our fields. This is the filtering in action. Is the kinetic energy for 100 kilometer, and on the right-hand side is the kinetic energy for scales smaller than 100 kilometer. And here we can see that the small scales are removed, while on the right we can see that the small scales is there and the large scales are absent. So this is a video from 2018 work. And now, using this coarse graining method, how do we define the wind work? How do we define the eddy killing? How do we define the separate the wind work at large scales and wind work at small scale? So with this coarse graining framework, we will define the power to the large scales as the dot product of the filtered stress tau and filtered velocity u. And power to the small scales is defined by this expression for EPCG here. So here, one thing we need to remember is that this EPCG does not represent the eddy killing to only length scale L. It represents eddy killing to all the length scales below L. So EPCG is the wind work on all the scales smaller than L up to how much this field is resolved. And this EPCG is an objective definition of wind work at scales smaller than L, as this is the actual term that goes into the budget equation. So this EPCG goes into the budget of eddy kinetic energy in the coarse graining framework. So this is the objective definition of the wind work at scales smaller than L. Now, using this framework, what do we get for eddy killing? We get the eddy killing estimation to be minus 50 gigawatt, and it works on a scale smaller than 260 kilometers. So all of the scales smaller than 260 kilometers are being killed, and the amount of the sink of the energy, the rate of the energy lost by the ocean is at a rate of minus 50 gigawatt. So how do we find this 260 kilometer and minus 50 gigawatt? We do scanning through a series of length scales from 0 to 1000. So first we choose this L to be 0. So when L is 0, there is no eddy. So we have nothing. It is 0. Now, as we increase L, this will start to include more and more eddies. Now, as we include more eddies, these eddies are being killed by the wind. Therefore, the value of EPCG falls to negative value. As we increase L more, it will start to include this EPCG term will start including more and more eddies, and these eddies are killed by the wind. Therefore, it keeps on falling, and it reaches to a maximum negative value at some certain length scale, and that is 260 kilometers. After that length scale, as we cross this scale, as we go larger than 260 kilometers, this curve starts to go towards positive value because the length scales larger than 260 kilometers are being forced positively by wind. So because of that, the wind work starts, this EPCG starts to include the positive work, and it starts to go towards higher values. And we say that this 260 kilometers is the length scale below which the wind kills the eddies, and above larger than 260 kilometers is the effective length scale above which the wind drives the ocean. So this can also be seen as a spectra, and from the spectra simply as a derivative of this EPCG term, and we'll see that at length scale of 260 kilometers, it crosses 0. For length scales smaller than 260 kilometers, it is negative, and for length scales larger than 260 kilometers, it is positive. So we say that the length scales smaller than 260 kilometers are effectively killed by the wind. Now the question is again, is the length scale same in all of the places? So we have plotted, so this plot here, the color map of the maximum length scale for eddy killing here for each of this point. And what we can see here is that the length scale is not same everywhere. Near the tropics, this point lies in around 900 kilometers. It's larger. And as we go towards higher latitudes, we find that this length scale is smaller. And in the core of the jet, it's smaller, and in the periphery, it's slightly larger. So the spatial distribution of the length scale for the eddy killing is not constant, and it is roughly related with the latitude. Now, why 260 kilometers? Why does the wind kill the scales less than 260 kilometers? To understand this, we again expand this EPCG. We follow the identities from IN 2005 and ALOI 2017 to write EPCG in terms of the prime terms, in terms of the high-pass filter terms. And we'll find this EPCG to have this expression. And here in this expression, what we'll see is it contains the, it is dependent upon the eddy kinetic energy, the small scale ocean current, the large scale wind, and the small scale winds. So this EPCG is dependent on these terms. And this EPCG is negative if this term is negative. So it is this term that is causing this EPCG to be negative. And there is a competition between this term and this term. So at the length scale, where the eddy kinetic energy dominates, the EPCG will be negative. And as soon as this term starts to dominate, as we come to the length scales, as we if we are at length scales where these terms are high, the correlation between these two terms, eddy in the atmosphere and eddy in the ocean, is starting to get highly correlated, then we'll start to have this EPCG go towards positive values. So this should be seen from the kinetic energy spectra of the surface kinetic energy of the ocean. So this is the energy spectrum for the Gulf Stream. And here we see that, and these vertical lines are the maximum length scale for the eddy killing. The orange one is for CSM data, and the blue one is for Avisho data. And we see here that this eddy killing length scale is very near to this peak of this kinetic energy spectrum. And the percentage here represents the amount of energy contained in the scales that are being killed by the wind. So the energy of the scales that are the energy of the scales that are being killed by the wind is 87% of the total kinetic energy. So most of the energetic eddies are being killed by the wind. Now, the seasonality of eddy killing. So we also, with the coarse graining, we have the freedom to calculate the wind work at each snapshot of time. So if we plot the time series, we'll see that the eddy killing has seasonality, and it peaks during winter, and it is correlated with the wind, anti-correlated with the wind. So here the purple plot is the wind, and the red is the eddy killing. And we see that this eddy killing is peaking during the winter when the wind is the strongest. So the seasonality of eddy killing is dominated by the seasonality of the winds. So, but we know that the mesoscale eddies itself are not energetic during the winter, but few months, approximately 3 to 6 months later. So why does the eddy killing peak in the winter, even when the eddies are not peaking in the winter? It's peaking somewhat later. So this has to do with, again, I come to the same expression for eddy killing here. So the variability of the large scale wind is wind velocity is an order of like 20 meters per second, and the ocean current is of 0.1 meter per second. So let's assume that this orange curve is the large scale wind. And this blue term, which has different peak time, be this term here. Now, if we multiply these two curves, we'll get the green curve, which represents EPCG. So the green curve here, this is normalized. And what we'll see that is the seasonality is governed not by the term in the blue circle here, but the term in the orange circle here. So it is because of the winds, the variability of the winds govern the seasonality of the eddy killing. So it is mostly, this is negative. This only determines if the eddy killing will be negative or positive, but this one is actually determining its magnitude and saying when it will be maximum. So now, how significant is this eddy killing? Well, in the global scale, eddy killing is like only around 5%. But if we look to the western boundary currents like Gulf Stream, Kuroshio, Oculus, Brazil, Malvinas currents, we'll see that the eddy killing is significant in comparison to the wind work at large scales. So in Oculus, it's even larger than the wind work at large scales. So this is pretty significant, especially in the dynamic regions. How about its comparison with other energy pathways? If we look into the other energy pathways, like the global kinetic energy to eddy kinetic energy conversion, we'll see even with baroclinic conversion, barotropic conversion, and inverse cascade, we'll see that the eddy killing is very comparable to the rest of the pathways of energy. So it is significant. Now, the resolution, back to the question of, because the ocean has longer time scales and shorter spatial scales, and the atmosphere has shorter time scales and larger spatial scales, we may want to sample the ocean less frequently, but in a high resolution grid, and we may want to sample more frequently in a more coarser grid. So will this resolution mismatch cause some problem, some biases in the wind work, estimation of this wind work? So we are not focusing on the time scales right now. We are only focusing on the length scales. So we are going to see how an ocean in a higher resolution grid, an atmosphere in a coarser resolution grid would affect this wind work. So we have the atmosphere grid in a coarser resolution and the ocean grid in a finer resolution. What we can do to calculate the wind work is we can, the wind stress, since is a function of the relative wind, we may want to, we will obviously interpolate the atmospheric grid to the atmosphere to the ocean grid, and then we'll calculate this tau like this. And if we do this, what we'll see is when the atmosphere, so the left one shows the data from QuickScat and Avisho, which are of 0.25 degree each, and the right one shows from NCEP 2, NCEP reanalysis 2, and this where the wind is 8 times coarser than the ocean. And we'll see that at large scales, the wind work, both qualitatively and quantitatively, if we see here from the figure, it's not much different. It's really indistinguishable just looking at this figure. And even if we look at the values of this wind work at large scale, it is very comparable. It's approximately the same. What about the wind work at small scales? At small scales, we see there is a huge difference. With QuickScat, we have smaller eddy killing, while with NCEP, we have larger eddy killing, almost 3 times larger eddy killing. So we are looking into what causes this larger eddy killing when we have NCEP winds. Is it resolution mismatch, or is it something else? So this also, it's seen in the plot of this EPCG versus L plot. We can see that for the coastal atmosphere for NCEP, this curve falls more lower than for the QuickScat winds. Similarly, we'll see that this curve seems like exact shift of this curve from the QuickScat winds. So this shows that this using NCEP wind has a systematic bias in having larger eddy killing. It's not that the eddy killing has the excessive eddy killing is seen just in bulk, but it is systematic. So it is happening every time, everywhere. So what causes this? So the answer is the small scales in the atmosphere. So let's say the atmosphere had small scales, which is represented by this small circular arrow here, and large scales, which is represented by this large brown arrow here, and a darker circular arrow is the oceanic eddy, and it has eddy killing of -8 gigawatt. And if the atmosphere lacks small scales and have only the large winds, then we'll have the eddy killing in this case on the right hand side to be more than the eddy killing on the left hand side. And this is also explained by partial re-energization in Renault's paper in 2016. So it doesn't only, it's not only the circular arrows, it's not only the co-located eddies, but also the gradients of the wind that can cause the small scale in the atmosphere to be present. So here on the left-hand side, if the gradients is like this, there will be less eddy killing than if the gradients are like this. So, but the gradients again can be represented as, so here the left-hand side, the gradient in the wind can be represented as the larger uniform wind, plus this small scale, which can again be replaced by the curl of the or a vorticity. So the gradient, in fact, is just again the same as having the small atmospheric eddy. So if a wind has gradient over winds, then we can say that there's a large scale wind and then an atmospheric eddy. And this presents an absence of atmospheric eddy because of the gradient will cause changes in the windward. So when the atmosphere is coarse, the gradients, the strong gradients are not well represented. The gradients are weak in the coarse resolution. And therefore, this is very weak or absent. And because of this, we'll have this exaggerated or spurious eddy killing. So we looked into this from toy data. We artificially created an atmospheric eddy co-rotating with this oceanic eddy and background uniform wind, and a case where it is not present. And we'll see that, in fact, when there is no co-rotating eddy, the excessive eddy killing is there. Now, it's not only this case. We'll see that this small scale atmosphere has more to do with not just presence and absence. So let's look to this term on the RAID here. And this is the term that actually determines if this EPCG is going to be negative or positive. And change this green term, which is the atmospheric eddy. Now, if we change the atmospheric eddy, we can see how this EPCG changes and how it affects the eddy killing. Now, we will choose a case where this dot product, this first term is negative. This will result in negative EPCG. So here we have for this to be negative, we have counter-rotating atmospheric eddy, and we'll see that this is minus negative. Now, the large-scale wind, if we add to the large-scale wind, the large-scale wind is only acting as a magnifying factor for this rate term here. So it will multiply this with the large-scale magnitude wind, and we'll get larger negative windward. Similarly, when we have this equals to 0, even when there is no wind at all, even if the atmosphere is stationary, there should be eddy killing because the current will experience drag. And if we add this large-scale wind, this will amplify this effect and cause more eddy killing. Now, what the case when this is positive, but this is negative? So this term is positive, but the term in the red is still negative. This will cause smaller eddy killing, and this effect will be magnified if we multiply with this large-scale wind. Now, a more interesting case is when this is equals to 0. So when this is equals to 0, we'll have atmospheric eddy and oceanic eddy of the same strength. And when oceanic eddy and atmospheric eddy are of same strength, we'll have this EPCG equals to 0 in absence of the background wind. But even with the background wind, even if we add a constant large-scale wind, we'll see that the eddy killing is 0. This is because the large-scale wind is only acting as an amplification factor to this rate rate part here. So this causes no eddy killing at all even when we have large-scale winds as well as small-scale winds. And what if this is greater than 0? When this is greater than 0, we'll actually have eddy energization rather than eddy killing. And then if we add background winds, this will be amplified and we'll have eddy energization rather than eddy killing. So it is actually the small scale atmosphere that governs the direction of the flow of the kinetic energy in the interface. And the large scale wind actually determines the magnitude. It acts as a magnification factor. So what has this to do with the spurious eddy killing? in the spurious eddy killing, we have this case, a co-rotating case because of the re-energization, because the atmosphere and the ocean is coupled, and it will have, there is more chances of co-rotating atmospheric eddy, because of which the eddy killing is reduced. While in ends of winds, because the ends of winds are coarse, this is not well resolved, or even the gradients. So the atmospheric gradients and the re-energization will cause the decrease of the EPCG, while in the ends of winds, because of weaker gradients in the wind and no small scale winds in the atmosphere, will have larger eddy killing, which we saw a few slides ago. Now, can we remove it? Is there a way to fix this? So turns out, yes, we can fix this. And how do we fix this? To fix this, let us rewrite the same thing again, but this time let's choose this L at the resolution of the winds. So when we choose this as the resolution of winds, we'll see that this, when we, instead of formulating wind stress as this, what we'll do is we'll filter in the resolution of the winds and calculate stress as this. And if we apply this, the application of this, it looks like this. Is again the atmospheric grid, the ocean grid. We interpolate the atmosphere. Now instead of calculating stress from here and here, we filter the ocean grid and make the resolution of the atmosphere and the ocean same, and we calculate the wind from these two, wind stress from these two. So, and this will result in a corrected wind work. So now here what we see here, this brown line is, or this dark brown line is the EPCG from the fixed stress, while this orange line is coming from the coarser atmosphere. So now we see that if we apply this method, we see that this can be fixed to by a very remarkable way. So to end this presentation, I'm showing you spectra from Storer et al. 2022, which shows the kinetic energy. So this is the ACC peak. This is the mesoscale peak. This spectra is again computed from the same coarse graining method. And the eddy killing acts on these range of scales. And on these range of scales, the wind work is positive. Now, what will happen if we have the atmosphere not resolved as the ocean? So let's say the atmosphere, the spectra of atmosphere looks like this. And because the atmosphere is not well resolved, it truncates here. Now, what will happen is the eddy killing will act, the correct eddy killing will act only in these length scales. And in these length scales, it will have spurious eddy killing. These length scales are killed more than it should have been. And it is because of this, we'll have spurious eddy killing. And it is, it's again the same case that I showed you a few slides ago. We have no small scales in the atmosphere, and if we have only the large scale winds, no small scale winds here. So this will cause spurious eddy killing. And this is systematic bias in the wind work at small scales. So, and I conclude this presentation with a few of the figures from previous slides. So the conclusion being the eddy killing happens below 260 kilometer. Eddy killing is concentrated in the active regions. The length scales for eddy killing is not same everywhere. The red term is the criterion for eddy killing, and this green term is the magnifying factor. There's a seasonality in eddy killing, and because of the mismatch in the resolution, we can have spurious eddy killing. which can be fixed, which can be reduced. The systematic bias can be removed, got rid of by our recipe. And thank you. And I'm open to any questions that you may have.
Thank you so much for this great talk. Yeah, let's open this up for questions. And maybe while people are thinking of questions, I'll ask about the initial results you showed with the Eddy killing. I guess that's the figure at the top center. And what I'm wondering how model dependent those results are.
I think yes. This the number, this 50 gigawatt, it would be more dependent on the models, maybe the kind of data set that we use. But we think that the length scale, this 260 kilometer, should not vary much whether what kind of models we use, because it is related with the energetics of the ocean. So the length scale for the Eddy killing census is governed by this this term here, minus UO prime, UO prime. Will have this pretty much near this value, even if we use different data sets. But we may have a slightly different value for 50.47 gigawatt. It may also depend on like at what range of let's say if we use 100-year data, we may not find exactly 50. Maybe we'll find 55. If we use one-day data, we are definitely not going to find 50 gigawatt if we are just taking one snapshot. We can find the same plot for one snapshot of data. And we are pretty sure that even for one day, we'll find this value to be near 260 kilometers. But this value may slightly different.
Great. We have questions in the chat, and then Mark Barras has raised his hand. So let me start with Jamie Pringle, who says he's in a public place and can't turn on his microphone. He asks, if we look at momentum instead of energy, do the asymmetries between cyclonic and anticyclonic Eddy numbers in some parts of the ocean lead to a net momentum flux into the ocean?
Yes, I think it's true. The cyclones and anticyclones are not. So I'd like to go to this slide here, and maybe it will be easier for me to explain. So if we look this here, so the wind gradient in the subtropics is like this, right? So we have westerly is more north, and the wind easterly is in the tropics. So the cyclones are being killed more effectively, while the anticyclones are trying to be energized. So if the gradients are strong enough, then it is possible that instead of having eddy killing, we can have energization of this eddy. But the energization, the magnitude of the energization will not be as strong as eddy killing, because we're again subtracting this UO bar, UO prime dot UO prime, and this will reduce the strength of this UA, the positivity of this UA dot UO here. So yeah, and yeah, this is actually a very nice question. Thanks for thanks, Zane, for asking this.
Very nice talk. Have you considered making a variable drag coefficient? Because in places like the Southern Ocean, it would change by a factor of 1.5 to 2 over the range of wind speeds. And that would obviously impact your first magnitude term, but it would have more implications beyond that. Have you thought about it?
We have not tried how the variability of the coefficient of drag changes. So this is a very simplification of the EPCG. Actually, in fact, CD itself depends on both this UA bar and UA prime. So, but this is a very non-linear relationship, and we cannot easily say how this CD will affect the eddy killing by this expression. But as long as we are using the bulk modulus of, as long as we are using the bulk formula of the wind stress, and I think this will not sense very significantly. Well,
it does.
Yeah, I don't know about how much the change in this is, but yeah, with this expression, we can't say for sure. Yeah, thank you for this question. Yeah.
You're welcome. Thank you.
Xuanting had a similar question in the chat. I don't know if you want to expand on that, Xuanting.
Oh yeah. I think this is question from Xuanting. How? Yeah, thank you again for asking this question. Yes, for this expression so far, the analytical expression of this here assumes that the CD is constant. I don't know how the CD varies with length scale. It of course varies with the wind velocity, and I don't know how much the bulk formulation of the wind drag varies with the scales, and at what scale this variation is high. The scale dependence of CD, I don't know much about that. So I think I don't know the proper answer to this, but yeah, it would be a future topic on which we could look into.
I guess it could depend on a little on the model, the numerical model you're analyzing, because there's a question how the numerical modelers have implemented this drag coefficient and whether they're using a constant coefficient or a varying coefficient. So I see that Tony Lee has raised his hand. Let's let Tony go ahead.
Hi, Shikhar. Thank you very much for your very nice seminar. The question about a graph that you show comparing the eddy killing curve from the observational base estimate that is using a VSO velocity and very quick scat wind. It's another one that has a vertical bar indicating the transition scale, comparing with CESM. I think it's before this slide.
Oh, okay. So you're talking about the spectra.
Yeah. Maybe the slide before the spectra. Yeah, that's the one. Yeah. So the difference between the blue bar and the vertical bar is, let's see, 260 versus smaller, right?
Yes. Well, this so here this is not the global. This is for Gulf Stream. So it's actually 200 and near 300. So this length scale is different for different parts of the ocean. So this is regional. So here, if we plot the same plot for global, it will be 216. But yes, it's 300 and it's nearly 220, 40, 250 around, something like that.
Okay, so it's not a huge difference whether you're using CSM versus the observational base estimate.
Yes.
Differ by 100 or so.
Yes.
Okay. All right. Thank you very much.
Yeah. Thank you.
Do you have any thought on, so setting the CSM aside for the observational based analysis, to what extent do you think the simultaneity of the observations impacts the scale transition? Probably doesn't matter much.
Yeah, Yes, so I think so. Right now, I am only looking to the mesoscales and of course the geostrophic component of the wind work. So if we simultaneously observe the wind and the ocean and look into more frequent observations and more high resolution observations, then I think this plot that I saw, there have been studies that says that at the scales like around 100 kilometer, there is a positive work, and that is coming from the inertial wind work to the inertial motion, right? So this curve would change, may change slightly as we start to include this inertial motions in our analysis. So yes.
Right, but it probably wouldn't change the transition scale by much, right?
Yeah, I think yes, should not change the transition scale so much with the geostrophic current.
Yeah, right. Thank you very much.
Thank you for your question.
Thanks. Christine has her hand up.
Oh, hello. Yeah, thank you very much. Really, really nice talk. Thanks. I've learned loads. I just wanted to ask also about the Aviso products, which you're using to determine essentially the scales of the ocean variability. And you say, you know, it's 1/4 of a degree resolution, but we know that the altimeters, or certainly the Aviso gridic products, don't really resolve ocean dynamics at scales less than about 100 kilometers. So,
yes.
So I just wondered, how is that affecting your results?
Yes. So how would that affect, and how is that affecting the results? Is the plot that I'm showing here, the length scale versus EPCZ. This plot here, this we see a constant linear kind of line here, and then there is this curve here. So this curve actually may not be as linear as we are seeing here, like this. It's below 100 kilometer. It's basically just the interpolation. It's basically just the diffusion kind of thing that we are seeing here. So this curve, we can say that around this region, like around 150 and above, the curve should look like this, but we are not sure about if the curve really looks like this below scales of 100 kilometers. So because we don't resolve that well, we cannot say if it's really like this. Maybe it is going towards positive value, or maybe it is more steeper, less steeper, so we cannot say for certain how the slope looks like.
Okay, because you showed very clearly the value of getting wind observations at smaller scales. So I just wondered how those results may help make the case for also current measurements at smaller scales.
I'm sorry, could you please repeat once again?
So you showed in what you presented that there is a lot of value in having better observations of the small scales for the winds.
Yes, yes.
So my question was, you know, how is there any evidence from this work also about the need for observation of the currents at smaller scales as well? And from what you just said, it seems that, yes, basically we know very little about that because of this limitation of the scales of the dynamics that we have now.
Yes, to your question, what I would want to say is when we have improper, when the winds are not well resolved, the method of this interpolating and calculating from here to here, the wind stress from here to here will result in the systematic bias. So it's actually the error there, and we can correct the error by calculating the wind stress from the same resolution atmosphere and the ocean current. And even when we have coarser atmosphere, when we calculate the wind stress from same resolution, wind and ocean current, the difference will not be as high, is what this plot is showing. So yes, indeed, we would really like to have more high resolution in both time and space for the more correct windwork estimation or studying the coupling. But as long as the mesoscales are concerned, and as long as we are looking only the geostrophic windwork, I guess the Eddy resolving ocean model and slightly coarser atmosphere with correction in the wind stress by filtering, getting the wind stress from the filtered wind ocean current should pretty much explain the eddy current without having very large biases. But if we forget and just interpolate the wind and calculate the wind stress from the interpolated winds, we are sure to find very high biases in the windwork in the small scales.
Thank you very much. Very interesting.
Thank you.
you.
Thank you for your question.
Thanks. I think we're just about out of time. But if there are no other questions, I wanted to quickly ask about the spatial variation of the length scale that you saw. And I wondered in particular, you have this global map of varying length scales. Does that scale with the Rossby radius in some way or with some other predictable parameter?
Yes, it's, I think you're talking about this figure here?
Exactly, yes.
Yeah, I think this, I would not say that the correlation between the length scale and the Rossby radius would be 1 or very high, but it has correlation, some correlation with the Rossby radius, because the energetics of the ocean itself is the highest growth rate. Length scale is itself dependent on the Rossby radius information, but it may also depend on the topography, because it will determine where the eddy kinetic energy would be more, and it may also depend on the circulation patterns, like in the recirculation patterns in the peripheries of the jets, the eddies come back and again re-enter. So this may give a larger scale flows, and which may be resisted by the wind and may be seen as the length scale of eddy. Yes, there are lots of things that would come into the length scale graph here. And of course, yeah, the Rossby radius deformation affects it.
Great. Well, thank you very much.
Thank you.
Thanks. So great talk, and thanks everybody for participating in a good discussion. I'm going to stop recording.